Hello YouTube and welcome. This is part 3 of my series, The Impossible Horizon, and it's subtitled Perspective Destroys a Flat Earth. Now in the previous two videos I've shown that the horizon that we actually observe is not really possible on a flat Earth in a number of ways. And today I want to look at the way that flat earthers claim a horizon is formed on a flat Earth, and ask the question whether that is possible or not. So flat earthers like to claim that perspective causes the horizon to form, in the same way that it causes a long corridor to appear to get narrower and shorter. And we've all seen pictures like this. And if the corridor was sufficiently long, then the wall at the end of the corridor would appear to end as a point rather than a square or rectangle. And that's because our eyes lack the ability to detect anything that occupies too small an angular size, and the figure that's often quoted is 0.02 degrees. Obviously, with any kind of magnifying device like a zoom lens on a camera or a telescope or even binoculars, you'd be able to see the wall at the end of the very long corridor again. But if the corridor was infinitely long, then you wouldn't see the wall at the end. It would end in a point. Now, if instead of imagining a very long corridor, you imagine a very wide floor and a very wide ceiling extending into the distance. And now, instead of a point, the floor and ceiling would eventually appear to meet in a line. And this is the argument that flat earthers make. And in a logical sense, it does make sense. As I said in the last video, it's not possible to produce a photograph and say, this is taken on a very large flat plane, the size of the Earth, and this shows exactly how a horizon should appear and should form on such a plane. You need to model in order to do that. So what we're doing is we're imagining that the ceiling comes all the way down to the red line here, and the floor comes up to the lower red line, and we see the end wall running from side to side across the screen. Now, it's probably easier to represent this in a diagram than a photograph. So here's a diagram of the photograph that we've just seen. We have ceiling, we have floor, we have two walls, and a blue wall at the end. And what I'm asking you to imagine is that there are no side walls at all, that the blue wall at the end extends right from one side to the other. And I've drawn some lines on to give the impression of things retreating into the distance. Make the corridor longer, and the blue wall at the end will get smaller in our vision, in our smaller angular size, and give us a narrower blue band across the screen. Make it longer still, and that band gets even narrower. Make it longer still, and it gets even narrower. And you can see that eventually it would end in a line across the screen. And this is exactly what flat earthers claim is happening on the plane of the Earth, that you can see far enough into the distance that you see the ceiling, if you like, the sky, meet the floor, that is the surface of the Earth. And today we'll think about ocean surfaces. So this is the sort of thing that we can see in reality. We have sky coming down, meeting the ocean, which rises up in our field of view, and a line across the screen where the two meet. So does that mean that perspective can create horizons that match reality? Well, you'll not be surprised to find out I don't think perspective can create horizons that match reality, but let's find out why. So looking in side view, we have our observer on a piece of land looking out over the ocean, and I've drawn a blue line to represent the sky, the height of the sky above the ocean. And there is a defined distance between the sky and the ocean. And the observer can see that distance just in front of them as an angle. Obviously, they're looking looking above their head, struck directly above their head and directly down. That angle would be 180 degrees. Here, I've drawn the angle from somewhere in front of the observer, and it's about 90 degrees. Now, as the observer looks at the sky and the ocean further away, that angle becomes much less. In this case, you can see it's considerably less than 90 degrees. And the same thing applies as we continue to look further away. The angle reduces. That may not be totally obvious in this picture, but it will become obvious later. And further away still, the angle is even less. And finally, with the arrow at the far end of the screen, I get the angle as small as I can draw it in this particular diagram. So you can see the angle reduces progressively. Our angle theta is getting less and less. What we're interested in is the point in time at which the angle theta becomes 0.02 degrees, because this will represent the point at which we can no longer see our band of, I don't know what color it would be, but our band between the sky and the surface, but we see just the surface and the sky appearing to meet. So when theta equals approximately 0.02 degrees, the sky will appear to meet the horizon. If we know the height of the sky above the surface, and we know we're looking for an angle of 0.02 degrees, we can calculate the distance to that point, the point at which the sky appears to meet the horizon. Now, on a cloudy day, the ceiling is the height of the cloud base. Now, here's a picture of a fairly uniformly cloudy day, overcast day, and we have a horizon and we have a cloud base. How high are the clouds? Well, I don't know for that particular picture, but we know different kinds of clouds have different altitudes, and we can do a calculation based on what might be a reasonable cloud base height for this particular observation. I've decided to go with the most favorable for flat Earth. I'm not sure whether what we're looking at there is stratocumulus at 4,000 meters, or whether it's nimbostratus at 2,000 meters or less. So giving flat Earth the benefit of the doubt, I've gone for nimbostratus, and I've even reduced the cloud base height to 1,500 meters. So assuming a cloud base of 1,500 meters, that's about 5,000 feet for people who can't think in meters, as might be the case for nimbostratus clouds. I'm plugging the numbers into the angular size equation. I've called the angle theta, the height between the clouds and the surface is h, and the distance that we are trying to calculate is d. So we plug in the numbers and we achieve or get a value for d, which is 4,297,183.289 meters, or 4,297 plus a few bits kilometers. That means on a flat Earth looking out over the ocean, the horizon should be about 4,300 kilometers away. And any object that is between us and the horizon, any object on the surface which is large enough, so say a mountain 5,000 feet high or 1,500 meters high, that mountain would be up to the cloud base. And if it was at any distance between us and the horizon, anything up to 4,300 kilometers away, we ought to be able to see it. And certainly if it was 2,000 kilometers away, it should appear to be there and be quite large in our field of view. You can do the calculation yourself if you wish. You find the angular size of an object 1,500 meters tall. But anyway, the law of perspective the flat earthers like to use to explain the existence of a horizon predicts that the sea and sky should appear to meet 4,300 kilometers away from the observer. Is that realistic? Well, many flat earthers realize that it is absolutely absurd to think such a thing. And just a digression, these wind turbines are 50 kilometers from the camera. They were visible with the naked eye. This is a slightly zoomed in image. But they appear to be sitting on the horizon. In fact, the bases of these turbines is beyond the horizon, partially obscured by the horizon, and they're only 50 kilometers away from the camera, not 4,300 kilometers from the camera. But anyway, many flat earthers realize that the distance to the horizon would need to be vast on a flat earth, and therefore they have an alternative explanation for why we can't see that sort of distance. And I've tried to represent that in this diagram. Just ignore the red arrow for the moment. It's an animation that hasn't quite, I've done it wrong. So we've got a cloud base, 1,500 meters, let's say, and an ocean observer looking out in this direction. And the arrow here indicates the decreasing visibility with distance. So what is happening here, and what is claimed by flat earthers, and I actually agree with them completely. I don't agree with their conclusions, but I agree with the explanation. What is happening here is that there are obviously air molecules close to the ocean surface. There will be an increasingly high number of water molecules. There may be some water droplets, some small aerosols. There may be particulate matter and various other things in between the observer and the far distance. All of these things can scatter light. So light coming from an object in the distance can be deflected and scattered, some of it reflected back, even towards an observer in the distance, and never reach the observer here on the left of the screen. The ambient light from the sun will also strike these molecules and particulates and aerosols and so on, and be scattered and deflected and refracted in various ways, and so some of which will reflect that light back towards the observer here, meaning that what you see is light that has come from another source and not light that is coming from the distance here. And as a result, for an observer at this elevation, there may be no visibility beyond this point. Now, as an explanation for why you don't see an indefinite distance when you look out across the ocean or even out across the land, this is perfectly valid. Visibility will vary even from hour to hour, certainly from day to day. Some days it appears clear and you can see a long way. Other days it appears less clear. If you have fog or mist, then even less clear and you can't see as far. This is something that people observe all the time. It's also worth bearing in mind that very bright or reflective objects or light sources in the distance will be visible over much longer distances than objects that are dull or dark, don't reflect much light. But as an explanation, it's fine. But what this means is that at the point at which we can no longer see any objects further than, say, this point, our cloud base and our surface have not yet met or appeared to meet, because they won't appear to meet until we are looking 4,300 kilometers into the distance. So what should we see if the Earth is flat and the light scattering and so on is reducing our visibility into the distance? Should we see something like this? Or shouldn't we see something like this? Shouldn't we see a clear band? Beyond this point, I can't see objects that are on the surface. I can't see objects, clouds, features in the clouds, like slightly darker areas or lighter areas, because my eyes just can't detect that light from that source, because they're seeing too much light coming from being reflected back to me from the particulates and the aerosols and so on in between me and the distance. Maybe it would look like this. Maybe it would be more of a gradient and maybe more of a dark color, perhaps even quite closely matching the cloud. But why would it always match the cloud? What if the clouds were uniformly white or uniformly very dark gray? Is it some magic coincidence that would cause the color of this band to match exactly the cloud color? And I've drawn it as a hard line here simply because I can't draw it as a gradual fade into the sky. Maybe it would be a brighter area, but with some sort of gradient going from top to bottom. Would it be a darker band going across the screen with not much light being reflected back towards the observer, but so much matter in between us and what we're trying to observe that light simply can't get through to us? But we never see things like this. In the real world, we see this. We see the sky and we see the surface of the Earth appear to meet. That's what horizon is. So it's normally defined as where the sky and the surface appear to meet. Now, I've, in an earlier video, slightly tweaked that definition to mean where the water on the surface might meet the land on the surface in our field of view as well. But that's not important. Where the sky meets the surface is a normal definition, or appears to meet the surface, normal definition of the horizon. And that's what we see. We actually see this. And this, I would say, is impossible on a flat Earth. Unless, of course, you think that that horizon is 4,300 kilometers away and you really can see all that distance. And as I've said, if that were the case, then any object that's large enough between us and 4,300 kilometers away should be visible. And of course, the 4,300 kilometers is with the naked eye. With a telescope, with a good P900 or some similar, you should be able to see the horizon much, much further into the distance. The horizon continues on to infinity in a flat Earth. Now, those who believe in the flat Earth might try and point to images like this one and claim that this shows a layer of, I've called it dirty air here. I'm not trying to be critical of that phrase. It describes it fairly well. It maybe shows a layer of dirty air filling the gap between the ocean and the sky. And that's true. I mean, that's kind of what we're seeing here. We're seeing, I guess, more light reflected back to our eyes from particles, molecules, whatever, in the atmosphere than is coming from the surface of the water or is coming from the sky further up above. And so we see this sort of hazy white fog, if you like, in the distance. And there are plenty of images like this. We do see this sort of thing from time to time. But we shouldn't ever be able to see this if the Earth is flat. Or this, or this, or this. These things are impossible on a flat Earth. And this image is perfectly possible on a spherical Earth as well. There's nothing about a spherical Earth horizon that says that air can't be sufficiently dense or dirty, have enough water vapor or water droplets in it and so on, that it becomes opaque effectively to the observer. You can't see through it. That's perfectly acceptable on a spherical Earth. But this and this and this cannot happen on a flat Earth. Unless you believe that these horizons are thousands of kilometers away. Here's a more greatly zoomed in picture. It hasn't shown the horizon climbing further up behind these wind turbines. You can see the turbines themselves, the blades are coming down to the water's edge, seemingly. The bases of those turbines are beyond the horizon, and we know that those turbines are only 50 or so kilometers from the camera. Now, it gets worse because I used a relatively low value for the cloud base height. And if the clouds were at 10,000 feet, the horizon would be even further away, be about 3 kilometers. Then there's the really, really tricky question of what causes the horizon on a flat Earth when the sky is cloudless or mostly cloudless, mostly clear. In such situations, we see a usually blue sky, and not at sunrise or sunset, but usually a blue sky, and it extends all the way down to the ocean. I've shown you some pictures like that. Now, it's not at all obvious to me at what altitude a clear sky forms a ceiling. And you must have a ceiling for the perspective-based model of the horizon, where the sky appears to meet the surface of the Earth. For that model of a horizon to work, you have to have a ceiling and a floor. We could maybe guess at an altitude. So one guess might be to say, to use the 100-kilometer imaginary line where the Earth's atmosphere effectively becomes very, so low it's considered to be in space. There is still atmosphere at that altitude, but it's not very much. You could use 100 kilometers, and when you do, when you plug 100 kilometers into the equation, you get a horizon distance of 286,479 kilometers. Nearly 300,000 kilometers. It's more than 3/4 of the way to the moon on the spherical Earth heliocentric model. It's not possible to have a horizon land, that far away, 286,000 kilometers away, appearing to meet sky in your field of view. I can't think of any flat Earth model that would think that's possible. Now, it might be a bit unfair to use 100 kilometers, so let's use 30 kilometers, about 100,000 feet, so that sort of height that weather balloons get to. And that gives us a distance to the horizon of 86,000 kilometers. It's still way too far. And the furthest part of any 2 points on the Earth's surface is 20,000 kilometers, or about 20,000 kilometers. It simply doesn't match, cannot match with reality. Now, what about, yeah, doesn't match with reality, impossible on a flat Earth. But what about a spheroid Earth? Well, the horizon is caused by something entirely different, not just perspective. The curve of the Earth provides a point from a given observation height and distance, a point beyond which you cannot any longer see the surface of the Earth. The Earth is curving away from the observer from this point onwards, and therefore cannot be seen by the observer. The surface appears to meet the sky at this point, but the sky that the observer actually sees will be away in the distance in this direction, and it's perfectly possible to calculate that distance as well. For our 2-meter high observer, the horizon here on the surface is at about 5 kilometers. And we can easily calculate, using a bit of Pythagoras' theorem, the distance from the observer to the horizon, and from the horizon to our 1,500 meter cloud base. And what we find is that on the surface, the horizon is 5 kilometers. So this point here is 5 kilometers. The sky that we're seeing appearing to meet the surface here is more like 138 kilometers further away. Total distance of 143 kilometers. And this provides quite an interesting little test, which is something that I may try to do. I'm not quite sure how I would try to set it up. But the test would be to have one observer here, a couple of meters above the ocean, have another observer at the distance to the horizon, so about 5 kilometers, and have them look straight up, vertically up. And do this on a day where we have clear skies and some clouds. And hopefully there'll be a cloud formation directly above their head, and the observer should be able to see that cloud formation well above the horizon. And if we had a third observer away 100 or so kilometers away, 143 kilometers away, a bit further because they're around the curve of the Earth, again looking straight up, that person should also be able to see a cloud formation directly above them, and be able to, the original observer, the first observer, should still be able to see that just at the horizon. that might provide a very interesting test for the spheroid or spherical Earth. But what is clear is that this kind of horizon is far more matching with what we observe in reality than the horizon on a flat Earth. The horizon on a flat Earth, the sky and the surface are appearing to meet, and they are the same distance from the observer. And they appear to meet with a 1500 meter cloud base at 4,300 kilometers away from the observer. If you want to plug in some larger numbers, for example, using a 30 kilometer, 100,000 feet altitude, and you get a total distance to this last bit of sky that you can see of 624 kilometers. Still a long distance. Obviously, we're using a clear sky for this 100,000 feet, so the test would need to be some kind of object, a plane or something, and I'm not sure we'd be able to magnify that enough to be able to see it. So testing this would be a little bit more difficult. But remember, on a flat Earth, we're talking something that's impossible, about 86,000 kilometers in distance. So in conclusion, what can we say? Well, the horizon that we see in reality matches what is expected on a spheroid Earth, and there have been so many tests of this, and it always matches what we expect. The distance to the horizon fits with the spheroid Earth model every time. And it's impossible on a flat Earth. So once again, we have to conclude that the Earth is not flat. And the most likely explanation is that it is a sphere or a spheroid with a radius of approximately 6,371 kilometers. Thank you for watching.